Welcome to Empowered Learning. This is the second video in the video series for reduction of order. And so this example is going to be a little longer than the ones that I did in the part 1 video. So I wanted to make a separate video for this one. And again, for this example, we're assuming that the y sub 1 that's given to us is a solution of the differential equation that we're given. And so we're just going to use reduction of order to be able to do it. Again, just to do some spot checks here, we know that since this equation equals 0 and we only have the second derivative, first derivative, and no derivative terms over here on the left side, and our coefficients here are either functions of x or constants, we know that this is a second order linear homogeneous equation. Okay, and that's important because we know that we can perform the reduction of order process on those types of equations. All right, so let's go ahead and get started here. So the first thing that we need to do is say that since we know what y sub 1 is, what is y sub 2 going to be? Okay, so here we're going to let y sub 2 just be u times y sub 1, which is just going to be u times x times sine of natural log of x here, where u is a function of x. Of course, that's important. All right, so now that we know that, we need to find out what y sub 2 prime and y sub 2 double prime is. Okay, so let's work on finding what y sub 2 prime is. So if we do y sub 2 prime, then this is just going to be the derivative of what we see here, and we're going to have to use the product rule. So I'm going to let u be my first function, so derivative of first times the second plus first times derivative of the second. And since I'm doing the product rule here, I'll take the derivative of the first here, so the derivative of x with respect to x is just 1. Plus x times, now we take the derivative of sine of natural log of x. And since that is a composition function, we'll use the chain rule. So this will be cosine of natural log of x. It doesn't look too hot, so let me fix that. And then times the derivative of the inside function, which is just natural log of x, which is just 1 over x. And so that is what our first derivative will end up being here. If we do a little simplification, not much to do. Here, this will just be sine of natural log of x here, plus, and this just will be cosine of natural log of x. All right, so we know what first derivative of y sub 2 is. Now let's figure out the second derivative. So for the second derivative, again, we'll be taking the derivative of both of these terms. So here, this will say the derivative of u prime, which is u double prime, times x times sine of natural log of x, plus, and of course now we'll just say u prime and then take the derivative of the inside function here, sorry, the derivative of the second function here. And of course that's exactly what we took the derivative of the first time whenever we were working to find what the derivative of y sub 2 was. Okay, and to be specific, I think it was about right here where we actually figured out what the derivative of x times sine of natural log of x is. Okay, because we said derivative of first times second, which was this first term here, plus up here, derivative of first times second, and so that's what this term was, plus first times derivative of second. So all this business here, which simplifies to this, is what the derivative of x times sine of natural log of x is. So saying all that to say that we want to reuse whatever we can instead of recreating the wheel here. Okay, and so that is what our second derivative here will look like for the first term. And so now what we need to do is take the derivative of the second term. Okay, and I want to make sure this is a u prime. So here we're going to say the derivative of u. So this is going to be the first, that's going to be the second. So we'll just do plus u prime and then just write what we have here. And then next we will have plus u. And so I will try to think of where I want to put this. I'll just put this, no, I put it here. So this will be plus u. And then we're going to take the derivative of what we have here. And I'm going to need to do that somewhere else. So let's switch this around. All right, so I'm just going to put this here. So it'll kind of be by itself. So remember, this term here is for the product rule, derivative of first times the second. And so now this is going to be the second part of that, which is first times derivative of the second. And so the derivative of sine of natural log of x will be cosine of natural log of x times 1 over x. And of course, the derivative of cosine of natural log of x will be minus sine of natural log of x times 1 over x. Okay. And so this will end up being all this will be, and I'll go ahead and try to simplify this. This will just be this same term here, but we'll combine these to make this 2 times u prime, and then of course write this as is. So I'm just going to pause the video, write that out, and then of course move on. All right, so now that we have this y sub 2 double prime written out, we can go ahead and just do a tally on everything. So we know that we're going to use this for y sub 2 double prime. We will use this for y sub 2 prime. And if we go way back up here at the top, we'll use this for y sub 2. And so now what we need to do is substitute all of that into our equation here, okay? And so we'll go ahead and start to write that out. So give us a little room. And then we'll go ahead and start writing it out. So therefore, our original equation was x squared times y double prime minus xy prime plus 2y is equal to 0. And again, since we are trying to solve for y sub 2, we want to put some 2's here just to remind us of that. And so now we go and substitute everything in. So for this first term here, this will be x squared times, and then all this business here for y sub 2 we're going to write in, okay? And I think I'll do this grouping symbol just to kind of make it different from what I have here. So this will be u double prime times x times sine of natural log of x here plus u prime, and this is 2 sine of natural log of x plus 2 times cosine natural log of x. And here we just have u with cosine of natural log of x all over x minus sine of natural log of x over x. All that's there. And so next we'll have the minus x here, and we're going to substitute in what y sub 2 prime is, which was this business up here. So this first term with the u prime times x times sine of natural log of x, we're going to put that under here, and then this term here we're going to put that under here. Okay. All right, so we have plus u prime and then x times sine of natural log of x. And then here we have plus u, and then this is sine of natural log of x plus cosine of natural log of x. Okay. And then lastly, we have plus 2 times, and that's going to be just this here. So it'll be u times x times sine of natural log of x. So this will be u plus u times x times sine of natural log of x. Okay. And so remember here that all this business here, so all this business here and all this business here is equal to 0. So what we need to do now is multiply this x squared into all these terms, minus x into both of these terms, and 2 into these two terms. And so we'll work on that now. So for this first term here, we'll have u double prime x squared times x here is going to give us x cubed times sine of natural log of x plus u prime here, and this will be 2x squared sine of natural log of x plus 2x squared cosine natural log of x. Close that. And then here, notice that we have x squared, and then in both of these terms, we're going to have an x in the denominator. So that's going to be a net x in the numerator. So this would be u times x times cosine of natural log of x minus x sine of natural log of x. Okay. And I think I forgot to do a grouping symbol here. Yeah. So I'm going to fix this and make that look correct. All right, so we'll have x here, and then we have that. Okay, so that is our first, this is first line here. So now we're going to do the same thing on the second line. And this would be plus u prime. And then the minus x times x here will be minus x squared sine of natural log of x. Okay. We close that. And then this will be plus u times minus x times this row here. So this will be minus x times sine of natural log of x. And then this will be minus x times cosine of natural log of x. Yep. Okay. And then lastly, we'll have this 2 being multiplied by what we see here. So this will be plus u, and this will be 2x times sine of natural log of x here. Okay. Close that out. And again, all this business here This ends up equaling 0. Now, at this point, one of the things that we are expecting to see is that all terms with u in it are going to cancel out with its other terms, so that all that ends up being 0. Okay, that's the first thing that we are expecting. And so we know that that's supposed to happen from the reduction of order process. So this is not anything that we're not expecting, because we do expect it. So here, if we look inside here, we're going to see that this should all work out here. Just going to confirm it. So here we have, since we got all u's here, we have a minus, let's say we got x times cosine of natural log of x, and we got a minus same thing, so that cancels each other. And here we got 2 of these minus x times natural log of x, and that cancels out with a positive 2x times natural log of x. So all that goes to 0 here. So we know that that works out. If we look here, we end up having, looks like a 2x squared sine of natural log of x with a minus x squared natural log of x. And so this should end up being an x squared sine of natural log of x, along with this 2 times x squared times cosine of natural log of x. All right, so let's write the simplified version of what all this is supposed to be now. And let me switch colors again. All right, so therefore we have u double prime of x cubed sine of natural log of x plus, and then here we're going to have u prime, and we'll combine these two terms to just be x squared sine of natural log of x plus 2x squared cosine of natural log of x. And since all these terms are 0, we just have equals 0 there. Now, at this point, what we want to do is we want to let v equal u prime and v prime equal u double prime. And I'm putting and here, but really, since v is going to be a function of x, then of course, if we take the derivative of a derivative, we're going to get the second derivative. And so that's why that would end up following suit there. So in this case, this would just end up being v prime. This would just end up being v. And so you can see now that we have reduced the order of our equation from order 2 down to order 1. And so that's part of the reason why the method is called reduction of order. Okay. So now if we keep on here, since this equals 0, we know from our steps of reduction of order that whenever we are doing this process on a linear homogeneous equation, and particularly the second order linear homogeneous, we know that we're going to end up with a separable equation. So what we are going to see here is that we will be able to get everything in terms of x on one side, everything in terms of v on the other. Okay. All right. So with that being said here, let's rewrite this equation and then try to get it into a separable form that will be easy for us to work with. Okay. So therefore, I'm going to write v prime as dv over dx because we'll need that later on. And this will be x cubed times sine of natural log of x here. And this v here, this will just be v x squared times sine of natural log of x plus 2x squared cosine of natural log of x. And that equals 0. All right, so from here, to make this look a little bit more simple, notice that all these terms here have at least x squared in them. So one thing that I can do to make this look a little bit easier is just divide everything here by x squared. And if I do that, then I know that x will not be allowed to equal 0. But if we look back at our original equation here, we see that that won't be possible anyway, because if x was allowed to be 0, I would no longer have a second order linear differential equation at this point, okay? And so it would no longer be of order 2 if x was allowed to be 0. As a matter of fact, it wouldn't be of order 1, it would just be some horizontal line, mainly y equals 0. And of course, we know that with these second order linear ODEs, that y equals 0 is always a solution to it, okay? So not anything surprising there. All right, so coming back here, if we divide both sides by x squared, then the result that we're going to get here is that we have dv over dx is going to be multiplied times x times sine of natural log of x here, plus v times, this will be sine of natural log of x here, plus 2 times cosine of natural log of x. And this equals 0. And so now what we need to do is just rearrange everything here so that we can get everything in terms of v on one side, everything in terms of x on the other. And again, this is v here. All right, so we're going to work on that now. So we'll have dv over dx. And we'll do this first term here. And we'll subtract all this from both sides. Oh, let's not do that. Okay. And so now here, if we rearrange, we'll have dv over v. And on this side here, we will have a minus sine of natural log of x plus 2 cosine of natural log of x. All of that divided by this x times sine of natural log of x. Okay. All right, so I'm going to simplify this right side sum here. So this, we're going to say this is minus 1 over x times, and then I'm going to work with the sine of natural log of x. So sine of natural log of x divided by itself will just be 1. And here I have plus 2 times, and cosine of natural log of x divided by sine of natural log of x will be cotangent natural log of x. So at this point here, we need to simply integrate both sides. So if we come here, let's make sure this is working. So integrate both sides here. So this will be integral of dv over v, integral of 1 over negative 1 over x, and of course all this business here. And this will end up looking like this. And of course, I think I forgot to write my dx. It's here, but it should be I lost that. Yeah, so here, whenever I rewrote all this, this should have been up here like that. So yeah, knew something looked funny there. All right, so here at this point, of course, we could take the antiderivative of 1, relatively simple, but here, remember, we got this -1 divided by x. So really what this is, and I'm going to go ahead and distribute this -1 divided by x here, is we have a minus integral of 1 over x dx, and then we have a -2 integral of cotangent of natural log of x all over x dx. Okay, so of course this integral here, easy to do, just going to be natural log of absolute value of v. This integral, easy to do, just negative natural log of absolute value of x. And here what we need to do is we're going to have to use the substitution rule here, and it's going to be relatively easy because we know that if we let natural log of x be let's say w, or I'm actually going to let it be theta, since just because it's inside of a cotangent function. If this is theta, then d theta is just going to be 1 divided by x dx. Okay, so I could deal with this and essentially say that this integral here is going to be the integral of cotangent of theta d theta. All right, so let's go ahead and write all that out and get to our next steps here. So we'll have, on the left side here, we'll just have natural log of absolute value of v. Of course, we'll skip this part and just go here. This will be minus natural log of absolute value of x minus 2 times integral of cotangent of natural log of x over this, and then we'll say let theta equal natural log of x. Then we know that d theta will be 1 over x dx. Okay, and then from that point, have natural log absolute value of v here equals need to erase this. All right, so that equals negative natural log of absolute value of x, and then this will be -2, and this will essentially just be cotangent of theta d theta, and that's because here the understood 1 right here divided by x dx is all going to be d theta, and then of course natural log of x is just theta. And so now from here, of course, we can integrate cotangent theta, and the antiderivative of cotangent theta is just going to be natural log of sine theta. And if you don't remember that, I'll actually do it the long way here and do the whole substitution rule thing. So here we could think about it like this, where cotangent, of course, is cosine over sine. And then from here, we'll say let w equal sine theta, which means that dw is going to be cosine theta d theta. And so, of course, all of this here is just going to be dw. This is just going to be w. And, of course, the integral of dw over w is just natural log of absolute value of w. So, continuing on here, have natural log absolute value of v equals minus natural log absolute value of x minus 2 times, and of course here we will go ahead and let this be dw w, And just working again on the right side here. And since now we're done with all of our integration for all terms, I'm going to go ahead and add another constant on there. And I think I was trying to see, have I already used C yet? So let me go back up here and see if I did. No, I didn't. Okay, that's good. So I can just go ahead and say this is plus C. And then I'll do a little more here. This will be minus natural log of X. We'll say plus. Well, no, let me actually do minus. Though. Don't want to mess up the signage there. So minus natural log of absolute value of W squared plus C. So now that I have that, I'm going to bring everything back together here. So from here, I have a bunch of natural logs here, and what I want to do is get everything on one side. So if I do that, this will be natural log of absolute value of V plus natural log of absolute value of X plus natural log of absolute value of W squared, and all that equals constant. And of course, when we add logarithms, that's the same as combining them all together and having what's on the inside of all of them be multiplied. So have this situation here. And then of course, to get this in a form to where I could use it, I can change this logarithmic equation into an exponential one. So this would just be, this equals e raised to the c. And here we see that because of our absolute value properties, that I can just drop the absolute value signs here, but do the plus or minus here. And we will say that all of this is just equal to A, where A is equal to, not going to have enough room there, but plus or minus e raised to the c. So here we will say A here is equal to plus or minus e to the c. All right, so from this point, we just need to solve for V. So therefore, we got Vx W squared is equal to A, which implies here that V is going to be constant A divided by X times W squared. And at this point, we can start subbing back in. Of course, W here was the same as sine theta, so this is going to be sine squared theta here, which this would be the same as saying A times cosecant squared theta all over X. And then of course our theta, if you remember that, theta, where do we have it? Yep, so theta here, this was natural log of X. So we'll just put all this in. This will be A times cosecant squared of natural log of X, all that over X. And so now we know what V is in terms of X. But remember here that V was equal to U prime, which is the same as du over dx. So this implies here that du over dx is going to be equal to A times cosecant squared of natural log of X, all that over X. And if we do some algebraic manipulation here, what we'll see is that du is just going to be A times cosecant squared of natural log of X, all that over X dx. And here we just need to integrate both sides again. And if we see here, we're going to have to deal with kind of the same thing we did up here in having to do the substitution so that we can deal with how we dealt with this cotangent of natural log of x divided by x. In that integral, we're going to do the same sort of thing here. Okay, so let's go ahead and work all of that out now. So here we have, let's see, therefore, integral of 1 du is just going to be u. And of course, over here, I'll take the a and factor that out. And we will keep all this other stuff on the inside here. And let's say and I'm going to use w this time. So let w equal natural log of x. And that would imply that dw is going to be 1 over x dx. Okay. So when we come here and this, so now the understood 1 divided by x dx, all that's going to be dw. And of course, natural log of x will just be w. So we'll just have cosecant squared of w dw. Okay. Now, if you remember here, whenever we take the derivative of cotangent, the derivative of that is negative cosecant squared of, whatever. So of course, if I'm having to take the antiderivative of positive cosecant squared, then that's going to be negative cotangent. Okay. So here we see that this is just going to be minus a cotangent of w. And this will be plus another constant. And I'll just call it, I think I've used c, so I'll just call it d here. And if you remember, w was natural log of x. Okay. And so this is what our function is, but I put natural log of w. That should be natural log of x. Let me change that. All right, so let's have some issues here. Okay, all right. And so that'll be natural log of x there. All right, and so the main thing here is that now that we have what this function u would be, we're going to say for simplicity, because remember, all we need is the root function for this. For simplicity, we're going to let u, which is a function of x, just be cotangent of natural log of x here. Okay. And if that's the case, then this implies that our y2 is going to be u times y1. Okay. And of course, our u here, we just said it was cotangent of natural log of x. And if you remember, our y1 way back in the beginning of the problem, let's go back there. Our y1 was x times sine of natural log of x. Okay. So we'll go and write that in. So x times sine of natural log of x. Okay. So finally here, what we see is that, of course, when we multiply cotangent times sine, if you remember, cotangent is cosine over sine, and multiply that times sine, the sines are going to reduce to 1, and what we have left is cosine here. So just get rid of that. So, of course, all of this, y2 is just going to be x times cosine of natural log of x. Okay. And so in knowing that, our basis of solutions for this differential equation And I'm going to write it in this form here so that you kind of get used to seeing it. It'll be x times sine of natural log of x. That is the first one, and x times cosine of natural log of x. This is the second one. And these two functions together, if we do any linear combination of these two functions, then whatever we come up with will also be a solution of our differential equation that we were trying to solve. So here, our general solution to our ODE is just going to be y of x is equal to C1, where C1 is any real number, times x times sine of natural log of x, and then plus C2, another real number, x times cosine of natural log of x. Okay, and so this would be, we did, again, any linear combination, which means if I take both of these functions and multiply them times, any assortment of constants, and I was to plug this back into my differential equation, I would see that it would satisfy. And so this is what we were looking for. So the answers that are important to us, we found what our other solution was, I'll say fundamental solution to our ODE here. Our basis of solutions is now complete. And again, since we had a second order linear ODE, we had to have two fundamental or base functions to create a basis or foundation for our solutions. And this is what our solutions would look like. Okay. And again, the C1 and C2 just mean that they're any real numbers, and this just means we're doing a linear combination of those two fundamental or base solutions. All right, so this will be the end of this video. I'm going to make one more video because I do have another example. It is slightly longer than this one, but again, in this last example, you're going to see a lot of things kind of get pulled together from other subjects to be able to solve a differential equation. And so you may not want to write that one down, but you at least probably want to watch it so that you can see all the things that I think of at this level that you should be prepared to deal with in solving a ordinary differential equation. So I'll see you in the part 3 video.